Hello and welcome to the second session of our CFD Master Class today. My name is Milad and I'm very happy to see so many participants again. And actually, I think you know this procedure. Before we will start to dive in our today's lesson, I would just like to make sure that the audio is working fine for everyone. So in the case you can hear me loud and clearly, please press the raise your hand button. Great, I already see some hands. Seemed like just waited for press the button. Great. In the case, guys, you know the game. Audio connections will drop for any reason. You can also use our toll-free audio service numbers to listen to the audio stream of this webinar. And for sure, we will record the session again and provide everyone with a recording just after this webinar. Okay, then let's take a look at our today's agenda. As you know, the second session is about result validation, which is a huge topic. So theoretically, I could talk hours and days about it. And basically, during the session, we will not only focus on how to validate results, but also how to improve the process of computation itself in order to increase the accuracy and reduce the computational demand for solving the simulation. And therefore, we will talk a little bit about some fundamentals you should know when you want to set up an advanced fluid flow simulation. And after that, I will demonstrate how you can use this knowledge, how you can utilize this knowledge in order to improve your simulation result quality. Just after that, I will present your homework for this week, and we have then for sure time for question and answers. If you have a question, just write it down into the question box and I will try to answer it as soon as possible. And since some people joined for the first time today, let me just quickly in 1 minute summarize what is the idea of this workshop series. So yes, basically we want to give the advanced users of SimScale to give them the opportunity to gain their knowledge about CFD and become real fluid flow simulation experts. And so the idea is to combine, let's say, fundamental knowledge and hands-on tips and tricks and really enable you to become or to develop to the next stage as a simulation engineer. And because some questions are asked again and again, yes, we will record all the webinar sessions. After this webinar sessions, we have 1 week time to submit an optional homework assignment, and everyone who will submit all 3 homework assignments will get a certificate of completion as well as free professional training with a value of 500 euro. Okay, then let's dive into our today's topic and talk about some really important fundamentals. And first of all, before we go into more details, let's just think about what is basically a CFD result. I mean, that's a good question. And the answer is a CFD result basically is nothing more or nothing less than, let's say, 2 vector fields. Oh, let me just quickly change my color. And let's first of all just assume that we would use analytic tools. Then our result, or what we want, is nothing more and less than a scalar field P depending on x, y, and z, which are our coordinates, and time t. And the same for velocity, so a vector function depending on x, y, z, and t. And that looks very abstract, but basically it's easy to understand. A fluid flow is completely described when I know for every point pressure and velocity. All other quantities, which we for example used during the last session, like turbulence, kinetic energy, K or omega, are just help quantities, additional help quantities, which are physically not necessary because pressure and velocity describes the fluid flow completely. So if I would have, let's say, a magic black box where I can put in my problem, like a CAD model of what I want to simulate, and it would give me back, let's say, 2 functions, I would have my result. A function where I can put in a combination of x, y, and z which describe a unique point in the field plus a time value, and that will give me the full exact result of my flow. The problem is, as you know, there is no possibility to get the analytic result. So we will never get back a function for x, for pressure and velocity depending on coordinates and time. What we get, because we are using a numerical method, is, let's say, a discrete list. Let's just call it list for the first beginning. A discrete list which includes p and the velocity vector for defined points at a given time. And this is what we basically do when we perform fluid flow simulations. And if you keep this in your mind, it will become easy to understand what result validation is about. Okay, just to summarize what we discussed right now. To describe a fluid flow completely, I would need pressure and velocity for every point for each time step. So I would have infinite number of values I have to store. If I solve these equations numerically, for example, using a finite development method we use for CFD on sim scale, I get discrete results. And so in the end, my CFD result is just, let's say, a list, a table, or a matrix, call it what you want, where I have pressure, velocity values, and maybe additional field values for every defined point. And if I have a time-depending simulation, I need this kind of list for every time step. And basically, so this is my CFD result, just a list of values. And what is the aim, or when is a result a good result? And therefore, we can take a look at three things. First of all, let's take a look at the so-called residuals here. This is just a plot, a residual plot I took for a random simulation. What you can see here is that here I have, on the x-axis, I have for all three charts iterations, and on the y-axis here I have residuals for velocity, pressure, continuity, k, and omega, which are all never in the end field values. And here we can see, let's say, the average error of my numerical method for every iteration. And this error becomes smaller and smaller. Here at about 50 iteration we have a kind of jump. Why we can get such jumps, we'll talk about that later. Or basically what we can just see here is the numerical error. So our aim is that all these lines go as down as possible, so that we have a minimum error for average error for all these quantities. And let's say here we can define criteria like it's converged, it's a validated result from a numerical perspective if all residuals are, let's say, for example, smaller than 0.01. And then this would be our criteria. And that, I mean, sounds fair. And if you take a look at your own simulation projects or simulation projects you can find in our library, you will see that most of the simulation residual plots for CFD are looking like that. So you may think, okay, fine, but this is not enough. Because what you should not forget, we have 3 steps. One step is that we turn an analytic into a numerical equation. The second step is that we, when you, for example, think about wall modeling turbulence, replace or, let's say, introduce physical models to calculate quantities in an easier way. And the third one is that I have, let's say, a physical correctness. And if my residuals are converged, it just means that my numerical method I used worked out and that I calculated a numerical valid solution. The problem is that, you know what I mean? The problem can be numerically correct, or your solution, but the physics can still be shit. Just to give you an example, if you choose, for example, wrong mole treatment, your residuals will look very great. Just remember the example from last week. But what is not looking great in this case, or are your force, or is your drag and also your lift. And that's the second thing you have to check. Do the forces converge? And sometimes what happens is the residuals are looking fine, but the forces are not like that, but maybe like that, completely crashing. And that means that for every step, your forces are changing massively. And the third thing you have to take a look at are fields. What do I mean with fields? Just imagine let's take a very easy example. You have again this fluid flow simulation of your airfoil. And forces means that in the end what we measure is constant. So forces are only applied on surfaces. The residuals are applied on the whole domain, and the field is like a residual which you just apply on one point. For example, you define this point here, or what makes more sense in general is, for example, the wing's ignition point, and then you just observe how the value at this point changes depending with the iterations. And if you want to be sure that your result is correct, residuals, forces, and fields should be converged. I see we have some questions already. One question if by Thomas, he asked if we can review all available SimScale result quantities related to vorticity and turbulence. Thomas, thank you very much for this question. I already got an email from you, I think, regarding that. I didn't forget it, but I just started to prepare something like a blog article, which I think is more helpful at this point. Unfortunately, we have not planned to talk too much during this workshop about turbulence, but since this it seems to be something a lot of people are interested in, I will discuss with my colleagues to prepare additional webinar just about turbulence modeling. I hope that's okay for you, Thomas. If you have some more dedicated or specific questions, just reach out to me and I will try to help. The next question is by Jose. Jose wants to know why the values of the residuals below 1e minus 4 is considered as a signal of good convergency, and what's the effect on residuals by changing the under-relaxation factors. Jose, you are again too fast for me. This is one of the next things I want to talk about, relaxation. Basically, what I wanted to point out when I talked about this residual convergence criteria. This criteria you can just define it, based on what you think makes sense. For example, for external dynamic cases, I say a good let's say rule is you should have at least a convergence below 1 e minus 5 for all field values. But for some other applications, like let's say transient simulations, you have other values. In the end, the residual you should just have like for yourself have a criteria like what convergence do you want to have and follow this approach. Okay, but let's continue. Okay, and now let's first of all take a look at what is actually happening when we are performing a fluid flow simulation. As you can remember from last time, the approach of most CFD solvers or of numerical CFD solvers is to divide your division you want to calculate into smaller subdomains, which allow us to solve the equation numerically, since we cannot solve the fundamental equations we have analytic way. And this is what we call division of domains, or what you will call meshing. And basically what we do is divide the whole fluid domain into small cells, and in the end we will just later on calculate values like pressure and velocity for the center of those cells. Let's take a maybe a little bit more detailed look what is exactly happening here. This is just a randomly picked, let's say, cell, three-dimensional cell. So this is our control volume, which has let's say different, we have it's made of 6 phases, sorry. And if you take a look, we have 4 equations. We can split it up 4 equations. We have these 3 equations, U, V, and W, which are the 3 components of velocity, and we have pressure. Everything is depending on coordinates and time. And basically, this is really the main idea of CFD and what these equations are based on, which we try to solve numerically, that 2 things are conserved, the mass and the momentum. And if you take a look at the mass, the meaning is quite easy. The difference of mass inside this cube is what is going in and out through the 6 phases. And if you write it down in a scientific way and simplify it, you will get this equation, which says in the end that the difference of what gets in and out minus the difference of what is changing inside the cell must be 0. And the second equation we have is doing the same for the momentum. Basically, it's all depending on, for example, for the mass, that velocity here multiplied with the area multiplied with the density is the volume flow flux inside. And based on this approach, you can define a numerical or equation system you can use to solve your equations later on. And basically, and this is I think the most important thing when we talk about CFD, even if we create the mesh, we still have this differential equation which we cannot solve. These 2 equations here, the Navier-Stokes equations. So what can we do? And there is something which can help us, which is called Gauss divergence theorem. And basically it says something very easy. It says it relates the flux of a vector field through a surface to the behavior of the vector field inside. So it allows us to calculate from the flux through the boundaries the flux change inside the cell. And if you think about it, if we now integrate based on this approach, which you can see here, so it says the volume integral of the divergence of vector field F integrated against volume is the same like the surface integral of F multiplied with the normal multiplied with d n minus y integrated over the surface. So it's just a relation between volume and surface integral. But this relation helps us in the end to transform our differential equations based on the mesh into a linear equation system. And the result is that all derivatives disappear and we have a linear equation system that we can solve with, let's say, standard numerical methods you may learn at school. And the final step is, which is iterated again and again, is to solve this linear equation system, and based on the solution you recalculate the linear equation system, and so you can iteratively calculate the solution you want. And so this is what we call in the end meshing, solving. This division of domain is what we would call meshing, and integration of cell is the step that is made to, in the end, to create a numerical equation system or linear equation system based on the mesh, which we can solve later on. We have some additional question. Josef wants to know that on page 9 of my presentation I'm not interested in the temperature field as well. Josef, you seem to be a very good observer. Yes, basically you also can add temperature field, just depends on your definition. For simplifying things, and because temperature field is nothing so important to understand the fundamentals, I decided to make all examples based on so-called cold flow, where we assume that temperature has no influence. But basically, if you say you have a hot flow, so where density can change and temperature can change, you would also have to add an energy equation. Okay. And this linear solver are very important because in the end they will mainly influence the performance of your simulation. And because maybe some of you are not so familiar with numerical methods, so let's just quickly talk about it. What means a solver? In the end, to make it very easy, you can just imagine the step of solving the linear equation system, it's like solving a standard linear equation system. You can see here. For sure, our equation system is much more complex, but basically you have a matrix, you have a vector which is unknown, which includes your solutions for x, y, and z. Don't forget, we need as many equations as unknown variables, and we know the result. And it's the same for our CFD calculation. You know this matrix A as well as this vector B were calculated during the meshing and this integration step. And now we want to know x, y, and z. And for our CFD simulation, in this vector, you will find for all the points velocity or pressure, and then it's again time dependent. But basically that's the idea. So, and what we want to get is a vector with components x, y, z, which is solving this equation system. And as you know, what is this basically saying? And basically, if you would multiply the first line, it would say x, 1x plus 1y plus 1z is 6. And 0x plus 2 multiplied y plus 5 multiplied z is minus 4. You know, that's the way we have to read these equation systems. And in the end, this step solving, and that is the first thing which is important for you when setting up your CFD simulation, is to choose the right method to calculate x, y, and z. From school, you may know very easy equation systems which you can solve using this Gaussian approach, where you try to get it into this special style of matrix, and then you can solve very easily. Just imagine the matrix would look like this. If your matrix is like this, it's very easy to know what x, y, and z is, because if your matrix looking like z, you know, and let's say this is 4, 6, 2, then you know that because 4z is 4, that z is 1. And this is what we call preconditioners. So the solver is generally going to calculate this vector. And preconditioners are transforming your matrix into a let's say into a condition which fits into let's say suitable numerical method. And basically this is when we talk about solver settings, what you will find later on also in SimScale. At solvers you decide which kind of approach you want to use to calculate this x, y, and z. We have on SimScale right now 3 solvers: GAMG for generic algebraic multigrid. This is an approach where we use a kind of coarser grid to smooth out high frequency errors. So let's say if our mesh is looking like that, what GAMG is doing, it's coarsening the grid, let's say, to the structure, and then calculating first this coarse solution and use this to reduce computation time. Another method is PCG. PCG stands for Preconditioned Conjugated Gradient Method, and which is only suitable for symmetric and positive definite matrices. What this means we'll talk later on. And the third thing we know type of solver are so-called smooth solvers. And for every application there is another solver I would recommend generally. For pressure you should use GAMG, because the way the pressure matrix, so this matrix for pressure we solve later on, is looking like, is that we have a big influence of this high frequency errors, and therefore this method for pressure can help to have a good result. And regarding the other two solvers, I would generally suggest to use a smooth solver, which is more stable for everything else. But generally, smooth solvers are more robust but taking more time, while PCG solvers are less robust but faster. And here for everything else, you should decide based on the quality of your mesh. So if you think this is a simulation which is really have a good mesh, easy boundary conditions, and you are quite sure it will converge without any problems, use smooth solver. If you're not sure, use PCG. Then the next thing, we talked about preconditioners, solvers, what are tolerances. This method, GAMG, PCG, smooth solvers, they're also iterative. So, for example, a good example is PCG. PCG, there you start with a random start vector. You get back a result, and based on this result, you calculate a preconditioner, which is modifying this vector in a way based on the error after solving this, and so by step it becomes better. And that's what we have talked about tolerances. You can not only decide when the solver should stop to calculate, but you can also decide when this solving loop should be stopped based on relative and absolute convergence criteria. Relative describes the difference between two solutions, between two steps, and absolute based on an absolute value. So for example, if I have, let's say, an error after iteration 1, I have an error of, let's say, 0.01, and after the second iteration I have an error of 0.005. Then I have a relative difference of 200 or of 2, and an absolute difference, the absolute convergence criteria is still 0.01. And as I mentioned, preconditioners are used to condition a given problem into a form that's more suitable for numerical solving. So we can use, so for every quantity I calculate, pressure, velocity, and maybe temperature, or K and omega, I have to define which solver I want to use to calculate it, which relative and absolute tolerance, and if I want to use preconditioners or not. Okay. Then let's go the next step. And Jose, you talked about relaxation. What is relaxation? And that's the next step. As you maybe can imagine now, a lot of things related to CFD depends on iterative approach. And the way we are calculating the new variable is not that we take only the old result, we are modifying it. As you know, we have this loop. We do an iteration. Let's maybe go some slides back to underline it. If we take a look at this loop, you can see I am taking the result as the input for the linear equation system to calculate the next result, which in theory should become more and more precise step by step. And how the new linear equation system, let's say, is calculated from the result, for this we use relaxation. So just imagine, at each iteration, you calculate a new value for each variable, each cell that's calculated. And the new value, which will be used for the next step, is the old value plus a factor multiplied with new value predicted minus old value. And this R is our relaxation factor. And we can control this factor, and within we can impact the solution or convergence time. If I have no relaxation, that means I use a factor of 1. We use the predicted value of the variable, because then V old and V old together become 0, V old minus V old, and this has like, and then let's say we have this average residual graph. If we use a factor smaller than 1, we will massively increase the stability. You ask maybe why? Because the change between these two iterations of the values becomes smaller, and since it becomes smaller, the chance is lower that we get in numerical trouble. The other option is to use so-called over-relaxation, where R is bigger than 1. This will accelerate the convergence, but decrease the stability, as you can see here. And based on this, you have to decide which relaxation value you want to use. And in the best case, you will use exactly that value that gives you still maximum convergence speed and is exactly at the point before starting to become instable. And yes, that's basically what we talk about. In general, most of the time you will use under relaxation, even for good mesh, and then you have to decide if you want to run 0.1 or if you can go up to nearly 1. And this is should depend on your mesh quality mainly. And if you have a good mesh, you need, let's say, less relaxation, and that's what we call relaxation. Okay, and now we come, let's say, to the last part. If you think about what we've talked so far, we talked about, first of all, how do we define convergence and how is this result calculated? And I mean, we talked about how we calculate the result based on the different iterations, but we did not talk about another problem. If we have discrete values between the points, then we need in the end to calculate the value between the phase, because otherwise we cannot run the simulation. And since we're using this discrete mesh, we have a problem because we don't need to know the value. We just need the value here and here. And therefore we use so-called schemes. They are in the end used to interpolate or also to calculate other stuff we need, like gradients, etc. And in the end, we have 3 properties for numerical schemes. First of all, the conservativeness, which means we must make sure that global conservation of the fluid is ensured on a local and global level. So we need between these two cells, we must make sure that mass and momentum is conserved as well for the whole system. Then the next thing is boundedness. Even if it's conserved, we must make sure that all values predicted by the scheme should, be within the realistic bounds. If we have like a very, 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 very high, let's say, pressure at one, for example, here, then it can still be the case that conservativeness is ensured, but some values are out of range. And the last thing is so-called transpositiveness, because between this layer, we in the end transport based on convection only in the flow direction, but based on convection, diffusion in all direction of the cells. And these are 3 things you should keep in mind. And basically, let's make it a little bit more hands-on. We will need the schemes to, for example, calculate between 2 cells. And now let me just introduce you 4 different concepts. Some of them are maybe not available at SimScale, but I think they will give you a good and vivid impression about what is possible. The easiest way of easiest scheme is so-called first order upwind scheme. And here the idea is very, very, let's say, easy, simple. And we just assume that the value of the phase here is the same value like at of the next upstream center value phase. So we say that for every cell we just take a look what's happening downstream, and for the value at the interface we just take the same value. So in this case, I have cell center here and a cell center here. Here my value is RE. Here my value is RP. And for the interface, I just took RE, first order upwind. And it's very robust, but the precision for sure isn't very bad. And this one is very well suited to start a simulation because it's robust. And just to make one step back, as you can remember at the beginning, we talked about convergence. And some of you may ask themselves, why is that happening? And what happened here is that we changed from first order to a better numerical scheme. And after we had the first kind of convergence, we just had a short jump, but after that, the other schemes were working fine. And if we would not have started with first order scheme, I'm quite sure the simulation would have crashed much earlier. Anyways. And a better solution is so-called central differencing scheme. And in the end, this is maybe the most intuitive way. The approach here is to perform a linear interpolation between the two cell center values. So again, I have my PE, so this is the cell center of cell E, cell center of cell P. I have the center value RP for P and the center value RE for E, and I just make a linear interpolation between them, and this is my value for the phase cell interface. And this approach works only for so-called local Peclet number larger than 2. Peclet number is similar to Reynolds number, a dimensionless number used in fluid mechanics, and it calculated of density, velocity, length divided by, I think that's d is not the diameter, but another dimensionless value, I think. And here you can also use a kind of hybrid approach, which use, for example, first order upwind when local Peclet number is too small and switches automatically to central differencing scheme. In the case it's necessary. And I mean, I think it's quite obvious that the central differencing scheme is better if it works. We have two other options, so-called power law and second order upwind. Power law is a complete, let's say, different approach. The power law, as the name says, the idea is that there is an analytic solution of the convection diffusion equation. And here we have like, let's say, a power approach, where we say RE, which we want to know, you can calculate it by RP, the value of the cell center downstream, and the value of the cell center upstream. And again, if a Peclet number is larger than 10, we have to use first order upwind instead. And another method is called second order upwind, which I suggest you to use most of the times, this one. And here we use another different approach. And here we do like two interpolations. We do interpolation from a cell. We have 3 cells instead of 2. This one, and this one. And here we do a linear interpolation from RW to RP and from RP to RE. And this combines accuracy and robustness, and this is what I would use most of the times. So use this whenever you can, and if you have really stability problems at the beginning, you can also should start with first order. Next question is by Gerasimos, and he wants to know, isn't the residual jump because something changed in the domain? In the airfall case, wouldn't this be the moment that the air from the right hits the airfall for the first time? Gerasimos, that's a very good question. And basically you're right. For sure, if you just see, sorry, if you would just see this graph here, you cannot really say what happens. For example, if you initialize with velocity 0 for the initial field, that can be, for example, the point where the air is hitting the wing, or where we have a flow separation, but it can also be related, and in this case it's really related to a change of the schemes. Okay, and finally, this kind of schemes are also used for something else. If we take a look at our Navier-Stokes equation, we can see a lot of, let's say, funny characters. And these are all mathematical characters. This is a derivate, this is a gradient, and nabla is a combination of gradient, derivate, and rotation. And we need these derivates for creating this linear equation system. But since we are working numerically, we have to do this also, calculate them also numerically. And therefore we use schemes which are working, let's say, with the same function principle like our numerical schemes for the interpolation. And there we have again first order schemes, higher order schemes, which we can use. Okay, then I would say we talked a lot about theory, and now let's try to convert this knowledge into practical knowledge. First of all, what will we do today? We will again take a look at a simulation of an airfoil. And in this case, you will not do the meshing yourself. I've prepared something. Let's open it and just take a look at that. And this will be, by the way, also part of your homework. So as you can see, we already have a mesh here and no geometry. What's the reason? The reason is quite easy. We just uploaded a ready mesh. And we use this special kind of mesh because for this demonstration, it really makes sense to do a 2D simulation. But since 2D has not really industrial relevance, we have not added this feature for meshing to the platform. And so if you can see, this is like a 2.5D mesh, what we call it. And this kind of mesh, it's easier to import them and create them locally. But since our focus is definitely not on the mesh, we can just jump this step and go to the simulation design. And what we will do right now is that we will, here you can see the airfoil. We will create a very easy simulation. Let me just prepare everything, where we will have a inlet here. We will have an outlet here. And let's make this maybe another color like black. This walls here will be treated like a symmetric wall because they should not interact with the simulation themselves. And this is maybe the most important thing, that for what you will see it later on, for these two faces, we use a special two-dimensional boundary condition. But since the mesh is finished, let's switch to the simulation designer directly and create a new simulation. So I will create a new simulation here. Choose fluid dynamics incompressible. Turbulence model is fine, steady state is fine, and simple for the solver is also fine. You may ask yourself, what is simple? We never talked about simple when we talked about solvers, and this is very important. As I told you, we use for every quantity a different solver. And pressure and velocity have to be linked somehow. And this linking of pressure and velocity, this is done over so-called pressure-velocity coupling. And this is what simple describes, a dedicated way of velocity-pressure coupling. Next step is to choose the mesh. I will just use the mesh we have created. And then you can imagine like last time, first of all, we have to add the material. So click on New. We'll choose the material from our library, click on Save, and add it to the volume. Initial conditions. Initial conditions, as you know from last time, they used for the very first iteration. And this is like our starting solution. And we can keep it like it is, because pressure and velocity 0 is okay. And K and omega, we can just use the default values. And now we have to add finally our turbulence, our boundary conditions. And let's start with that. Let's start with inlet, which is this phase. And we will define there a fixed value for 30 meters per second in x direction and apply it on this phase. Then we can continue with the outlet. Here the type is pressure outlet. This is fine. Next thing, and this is something Levi asked, why I'm using not slip wall instead of symmetric. Because I don't want this to act like a wall. I want it like to act that it's open here. And slip wall, the difference between slip wall and symmetric is that symmetric is also applying this zero gradient symmetric conditions not only for pressure but also for velocity. Here we will use top and bottom. And what we also need for this, let's call it 2D. Here we'll use a custom boundary condition 2D empty, which means that we want to perform a 2D simulation. And finally, for the airfoil itself, type wall, a no-slip wall, and choose the airfoil. Okay, and then we're basically done. We just have to define how many iterations we want to perform, 3000. We want to write out only the final step. And since we are performing a 2D simulation, we just use one core. And increase the maximum runtime. And basically our simulation is now finished. And what we will do right now, we will create a simulation one. Let's call it default settings as a reference. And now, for example, we can start to modify numerical settings and see how this will affect our solution and solution time. And let's just quickly review the settings we have. Under properties, you can find the relaxation factors here. Here you can choose which solver you want to use for pressure, velocity, turbulent kinetic energy, and omega. And you can take a look. Here then you can define the absolute, the relative tolerance, and as you know, GAMG comes without a preconditioner, so we cannot choose it, but here for you PBICG or PCG with general family of this kind of solvers, we can even use a preconditioner. And the numerical schemes can be changed here. So here you can see how our gradients, for example, are computed. You can see how divergence schemes are computed, Laplacian operators are computed, and how interpolation is done. And this linear is basically what we call first order, and we have even higher standards. Okay, and what we will do right now, we will, and this will be part of your homework also, vary different numerical settings and see what will happen. For example, what we can do right now here is to change the total tolerances, or to change the relaxation for pressure, making it, for example, 0.1, create a new run, Then, for example, you know, just if you want to increase it to, let's say, 0.3, you can again create a new run. And so on. And finally, you just have to start the simulations, and later on we can compare the results. And if you do that, I've prepared a project including the results. You will have a lot of simulations. And for example, here, you can see all the runs I've created. For example, here, for example, we have for different relaxations. Take a look at them, and then you can see, for example, the different convergence plots. And if we have relaxation like 0.6, you can see that your simulation will crash. Okay, and I mean, let's take a look what we did so far. So we created a general setup for the simulation. Basically, most of the steps are the same. We assign a mesh, we define a material, define initial and boundary conditions, and really here it's important to define this, but only for the 3D simulations, this two-dimensional boundary condition. And just because some people ask what is different between 2D and 3D, basically the difference is that 2D means your stuff is only depending on X and Y. But you can basically perform exactly the same way of post-processing. So let's take a look at the solution field. The result will still look like 3D, but it's pseudo 3D because it's 2.5 dimensional. You have not really a third dimension. But here you can basically perform exactly the same kind of post-processing. The only thing which will not really work are streamlines, I think. But for example, here, you can see, for example, you can see it here, velocity distribution. You can just create a slice to make your work easier. Yes, like you know it basically. Okay. And oh, maybe one interesting thing. As I mentioned, you can do basically the same post-processing like for 3D cases. What we never talked about is that you can take a look also at the logs. And for example, if we take here a look, the simulation was finished after 800 iterations. Why using a higher relaxation factor, there's a simulation is not finished after 887, but after, oh, sorry. Here, for example, oh, once is crashing, maybe that's not the best idea, but here, for example, it's finished after 900 iterations. And the reason is related to our tolerances. If you take a look here, it's a solver log. You can see that simple solution converge. That means that one of our convergence criteria defined before was reached. And here, it converged after 9 iterations. But basically, the setup was for 3000, so it really shows the impact. Okay, then I think we can now introduce I will now introduce you to your homework, and we have time for question and answers. Let's just a question I would like to answer by Muhammad. He wants to know if the default quantities for schemes are good for solving different type of problems. Muhammad, basically the default settings were chosen in a way that they work for most of the cases, but I would suggest if you know your simulations maybe a little bit more special, you should take a look at the library, look for a similar simulation, similar kind of physics, and then maybe copy the numerical settings or just write in the forum. Okay guys, your homework will be to investigate the influence of different numerical settings on convergence behavior of a simulation yourself. This is, for example, the compared convergence graph for different relaxation levels. And from tomorrow, you will find a step-by-step tutorial on our website. I will send also email to you. This step-by-step tutorial includes the mesh and the instruction how to set up the simulation, what to modify. And you have 1 week time to submit this homework. Okay, great. Then we have no time for question and answers. You asked a lot of questions during the session, so most of them are already answered. And if you have a question, just write it down and I will try to answer it. And okay, there seem to be not so many questions, just some of you saying that it was a good webinar. Thank you for this feedback. It's really great. It was a lot of fun. I would suggest just wait until I send you the link to the recording and the homework till tomorrow. And then you can maybe look again at the record, and if you have questions, just write it to the forum. Then Pramod asked what exactly mesh singularity means. Please also give some tips to overcome this problem. Pramod, I think you're talking about FEA. The singularity problems are not related to CFD in general. Singularity, to explain in an easy way, means that your mesh was finished but something is wrong with the mesh structure. But if you're interested in that, send me an email or write in the forum, we'll answer but this is, as I mentioned, not related to CFD. Okay guys, seems to be all the questions. Hope to see you next week. It was really great to have you here. Have a nice week. See you soon. Bye.